Okay, on the handout of the example problems, we are going to work through the odd problems, and you're going to be given some time to work through the even ones. So in number 1, in September of 1998, the population of the country of West Goma in millions was modeled by f of x is equal to 17.8 times e raised to the 0.0016 to the x power. At the same time, the population of East Goma in millions was modeled by g of x is equal to 14.1 times e raised to the 0.0106 x power. In both formulas, x is the year, where x equals 0 corresponds to September of 1998. Assuming these trends continue, estimate what the population will be when the populations are equal. So in order to do that, what you are going to do is you're going to set these two functions equal to each other. So I have 17.8 times base e raised to the 0.0016 x power is equal to 14.1 times base e raised to the 0.0106 x power. Now, at this point, in order to adequately solve the equation, you're going to have to rewrite both sides as a logarithm. So when I do that, it requires more algebra than it's worth. So what I would advise that you do is you put both of these into your calculator, and then you go to your table of values. And when you go to your table of values, you are looking for the x value that gives you the same y value. So in your columns, you have x to your left-hand side in your table, and your second column is going to be the y values of your first function, and the third column will be the y values of your second function, and you're looking for when those y values are equivalent to each other. And that is going to occur at 19 million. Okay, 19 million. So your populations are going to be equal to 19 million when they are equivalent. For number 3, it says the population of wolves in a state park after 2 years is modeled by the function p of t is equal to 900 divided by 1 plus 99 times e raised to the negative 0.3t power. What was the initial population of wolves? What was the initial population of wolves? Well, if you pull out the fact that you have this 1 over e to the negative 0.3t, then what you're going to have is 900 over 100, essentially, because this is going to be very small. And so 900 divided by 100 is going to end up giving you 9. So your initial amount, your P naught is what you're looking for, is going to be 9. Another way that you can go about looking at that is if I substitute 0 in for time t, which is going to be my time 0, then when I put 0 in here, anything raised to the 0 power is going to be 1. So 1 plus 99 is going to be 100, and 900 divided by 100 is going to give me 9. Take a look at number 7. Suppose the algae growth in Black Oak Lake increased from 100,000 cells per milliliter to approximately 10 million cells per milliliter in a 7-day period. The specific growth rate R is defined using R is equal to log of n sub 2 minus log of n sub 1 divided by x2 minus x1, where N1 is the algae concentration at time x1 and N2 is the algae concentration at time x2. In this situation, what is the specific growth rate of algae? Round your results to the nearest hundredth. So we know that N1 is 100,000 and N2 is 10 million. So R is equal to log of 10 million minus log of 100,000 divided by, and we know that the x2 minus x1 is 7 days, okay, because they tell us this occurred over a 7-day period. So I'm going to divide this by 7. And when you put this into your handy dandy calculator and let your calculator do all the work, then you're going to end up with R is equal to 0.29 when we round to the nearest hundredth, which means our growth rate is 29%. On the same handout, take a look at number 11. It says, what is the intensity in watts per meter squared of a noise measured at 78 decibels? And they tell you that the level of sound intensity in decibels is beta is equal to 10 times the log of I over I naught, where B beta is the number of decibels, I is the sound intensity, and I naught is 10 to the negative 12th watts per meter squared, round to the nearest tenth. So what we're actually solving for in this is I, because they tell us the number of decibels. We have 78 is equal to 10 times the log of I over 10 to the negative 12th power. And so in order to solve this, we have to use those properties of logarithms that we talked about 2 days ago and yesterday with the equations. So I have 78 is equal to 10 times the log of I minus the log of 10 to the negative 12th. And so I'm going to distribute, or I can go ahead and divide by my 10, and this gives me 7.8 is equal to log of I minus log of 10 to the negative 12th. And so in order to get rid of my 10 to the negative 12th, I'm going to add it over. So this gives me log of I is equal to 7.8 plus log of 10 to the negative 12th. And to undo the logarithm, I have to exponentiate it. And so in this case, my log has a base of 10. So I am going to have I is equal to 10 raised to the 7.8 plus log of 10 to the negative 12th power. And when you put that into your calculator and you let the calculator do all of the fancy legwork, then it is going to give you an answer in scientific notation. And so with that scientific notation, that E on the end of your answer means 6.31 times 10 to the negative 5th power watts per meter squared. Okay, take a look at 13 in the next video because I only get 10-minute intervals. So when you start the next video, we will pick back up at number 13 and finish off the rest of the examples for you to work in class.